Rotational motion, circular motion, rotational equilibrium, and now rotational motion. Describe how the rotational inertia of an object affects how easily the rotational speed of the object changes. List the three principal axes of rotation in the human body. Describe what happens when objects of the same shape but different sizes are rolled down an incline. Explain how Newton's first law applies to rotating systems. Describe what happens to angular momentum when no net external torque acts on an object. Explain how gravity can be simulated. The big idea. Rotating objects tend to keep rotating while non-rotating objects tend to remain non-rotating. In Chapter 3, you learned about inertia. An object at rest tends to stay at rest, and an object in motion tends to remain in motion in a straight line. Newton's first law of motion. In Chapter 8, this concept was extended when you learn about momentum. In the absence of an external force, the momentum of an object remains unchanged. Conservation of momentum. In this chapter, we extend the law of momentum conservation to rotation. Discover what makes an object easy to rotate. Try balancing a 12-inch ruler upright on the tip of your finger. Mold a large ball of clay around one end of the ruler. Try balancing the ruler on the tip of your finger with the clay on top of the ruler. Now try balancing a pencil and then a meter stick on the tip of your finger. Analyze and conclude. 1. Observing. How did the addition of the clay affect your ability to balance the ruler on the tip of your finger? Which was easier to balance, the pencil or the meter stick? Predicting. Which would be easier to rotate back and forth, a meter stick held at its center with balls of clay at the ends of the meter stick, with balls of clay near 40 centimeters and 60 centimeter marks? Making generalizations. How does the distribution of mass in an object that is easy to balance affect its tendency to remain balanced? 12.1. Rotational inertia. Newton's first law of inertia also applies to rotating objects. In every case in which an object is rotating around an internal axis, the object tends to keep rotating about the axis. Rotating objects tend to keep rotating, while non-rotating objects tend to remain non-rotating. The resistance of an object to change in its rotational motion is called rotational inertia, sometimes called the moment of inertia. The greater an object's rotational inertia, the more difficult it is to change the rotational speed of the object. When swinging your leg from your hip, why is the rotational inertia of the leg less when it is bent? The rotational inertia of any object is less when its mass is concentrated closer to the axis of rotation. Can you see that a bent leg satisfies this requirement? Just as it takes a force to change the linear state of motion of an object, a torque is required to change the rotational state of motion of an object. In the absence of a net torque, a rotating top keeps rotating, while a non-rotating top stays non-rotating. Rotational inertia and mass. Like inertia in the linear sense, rotational inertia depends on mass. But unlike inertia, rotational inertia depends on the distribution of the mass, as illustrated in Figure 12.1. The greater the distance between an object's mass concentration and the axis of rotation, the greater the rotational inertia. The tightrope walker shown in Figure 12.2 increases his rotational inertia by holding a long pole, allowing him to resist rotation. Rotational inertia depends on the distance of mass from the axis of rotation. Easy to rotate, difficult to rotate. By holding a long pole, the tightrope walker increases his rotational inertia. Consider where the center of gravity is being adjusted to. A long baseball bat near its thinner end has more rotational inertia than the short bat of the same mass. Once moving, it has a greater tendency to keep moving, but it is harder to bring it up to speed. A short bat has less rotational inertia than a long bat, and it's easier to swing. Baseball players sometimes choke up on a bat by grasping it closer than normal to the more massive end. Choking up on the bat reduces its rotational inertia and makes it easier to swing up to speed. A bat held at its end, or a long bat, doesn't want to swing as readily. Similarly, as illustrated in figure 12.3, the short pendulum has less rotational inertia and therefore swings back and forth more frequently than the long pendulum. Figure 12.3, the short pendulum will swing back and forth more frequently than the long pendulum. Consider the figure carefully. Long-legged animals such as giraffes, horses, and ostriches normally run with a slower gait than hippos, dachshunds, and mice. The Chihuahua, shown in figure 12.4, runs with quicker strides than his longer-legged friend. It is important to note that the rotational inertia of an object is not necessarily a fixed quantity. It is greater when the mass within the object is extended from the axis of rotation. Figure 12.5 illustrates how you can try this with your outstretched legs. Swing your outstretched legs back and forth from the hip. Now do the same with your leg bent. In the bent position, it swings back and forth more easily. To reduce the rotational inertia of your legs, simply bend them. Figure 12.4, for similar mass distributions, short legs have less rotational inertia than long legs. Figure 12.5, you bend your legs when you run to reduce their rotational inertia. That's an important reason for running with your legs bent. Bent legs are easier to swing back and forth. Formulas for rotational inertia. When all the mass m of an object is concentrated at the same distance r from an axis, as in a simple pendulum bob swinging on a string about its pivotal point, or a thin wheel turning about its center, then the rotational inertia I equals mr squared. Note, rotational inertia depends very much on the location of the axis of rotation. A meter stick rotated about one end, for example, has 4 times the rotational inertia that it has when rotated about its center. When the mass is more spread out, as in your leg, the rotational inertia is less and the formula is different. Figure 12.6 compares rotational inertias for various shapes and axes. It is important for you to learn these values, but you can see how they vary with the shape of the axis. How does rotational inertia affect how easily the rotational speed of an object changes? Figure 12.6, rotational inertias of various objects are different. What is the easiest way to rotate your pencil? Flip your pencil back and forth between your fingers. Compare the ease of rotation when you flip it about its midpoint versus flipping it about one of its ends. For a third comparison, rotate the pencil between your thumb and forefinger about the pencil's long axis. So the lead is the axis. Study the three cases shown in figure 12.6. Think in which case is rotation easiest. In this case, is the small rotational inertia consistent with the small r? 12.2, rotational inertia and gymnastics. Consider the human body as shown in figure 12.7. You can rotate freely about three principal axes of rotation. The three principal axes of rotation in the human body are the longitudinal axis, the transverse axis, and the medial axis. Each of these axes is at right angles to the other, mutually perpendicular, and passes through the center of gravity. The rotational inertia of the body differs with each axis. Figure 12.7, the human body has three principal axes of rotation, such as the three axes, X, Y, and Z. Same idea. You just have to be able to name them. Longitudinal axis. Rotational inertia is least about the longitudinal axis, which is the vertical head-to-toe axis, because most of the mass is concentrated along this axis. Thus, a rotation of your body about your longitudinal axis is the easiest rotation to perform. An ice skater executes this type of rotation when going into a spin. Rotational inertia is increased by simply extending a leg or an arm. The skater has the least amount of rotational inertia when her arms are tucked in, as shown in figure 12.8a. Note, there's plenty of physics in sports. Figure 12.8, an ice skater rotates around her longitudinal axis when going into a spin. The rotational inertia when both arms are extended, as in figure 12.8b, is about 3 times more than in the tucked position. So, if you go into a spin with outstretched arms, you will triple your spin rate when you draw your arms in. With your arms extended as well, as in figures 12.8c and 12.8d, you can vary your spin rate by as much as 6 times. We will see why this happens in section 12.5. Transverse axis. You rotate about your transverse axis when you perform a somersault or a flip. Figure 12.9 shows the rotational inertia of different positions from the least when your arms and legs are drawn inward in the tuck position to the greatest when your arms and legs are fully extended in a line. The relative magnitudes of rotational inertia stated in the caption are with respect to the body's center of gravity. Rotational inertia is greater when the axis is through the hands, such as when doing a somersault on the floor or swinging from a horizontal bar with your body fully extended. Figure 12.9. A flip involves rotation about the transverse axis. A. Rotational inertia is least in the tuck position. B. Rotational inertia is 1.5 times greater than in the tuck position. C. Rotational inertia is 3 times greater than in the tuck position. And D. The gymnast's rotational inertia is 5 times greater than in the tuck position. In figure 12.10, the rotational inertia of a gymnast is up to 20 times greater when she is swinging in a fully extended position from a horizontal bar than after dismount when she somersaults in the tuck position. Rotation transfers from one axis to another. from the bar to a line through the center of her gravity, and she automatically increases her rate of rotation by up to 20 times. This is how she is able to complete 2 or 3 somersaults before contact with the ground. Figure 12.10. The rotational inertia of a body is with respect to the rotational axis. A. The gymnast has the greatest rotational inertia when she pivots about the bar. B. The axis of rotation changes from the bar to a line through her center of gravity when she somersaults in a tucked position. Medial axis. The third axis of rotation for the human body is the front to back axis, or medial axis. This is a less common axis of rotation and is used in executing a cartwheel. Like rotations about the other axes, rotational inertia can be varied with different body configurations. Concept check. What are the 3 principal axes of rotation in the human body? 12.3. Rotational inertia and rolling. In figure 12.11, which will roll down the incline with greatest acceleration, the hollow cylinder or the solid cylinder with the same mass and radius? The answer is the cylinder with the smaller rotational inertia. Why? Because the cylinder with the greater rotational inertia requires more time to get rolling. Remember that inertia of any kind is a measure of laziness. Which has the greater rotational inertia, the hollow or the solid cylinder? The answer is the one with its mass concentrated farthest from the axis of rotation, the hollow cylinder. So a hollow cylinder has a greater rotational inertia than a solid cylinder of the same radius and mass, and will move lazy in gaining speed. Figure 12.11. A solid cylinder rolls down an incline faster than a hollow one, whether or not they have the same mass or diameter. The solid cylinder will roll with greater acceleration. Interestingly enough, any solid cylinder will roll down an incline with more acceleration than any hollow cylinder, regardless of mass or radius. A hollow cylinder has more laziness per mass than a solid cylinder. Objects of the same shape but different sizes accelerate equally when rolled down an incline. You should experiment and see this for yourself. If started together, the smaller shape, whether it be a ball, disc, or hoop, rotates more times than the larger one. But both reach the bottom of the incline in the same time. Why? Think. A heavy iron cylinder and a light wooden cylinder, similar in shape, roll down an inclined plane. Which will have more acceleration? The cylinders have different masses but the same rotational inertia per mass, so both will accelerate equally down the incline. Their different masses make no difference, just as the acceleration of the free fall is not affected by different masses. All objects of the same shape have the same laziness per mass ratio. Would you expect the rotational inertia of a hollow sphere about its center to be greater or less than the rotational inertia of a solid sphere? Defend your answer. Greater. Just as the value mr squared for a hoop's rotational inertia is greater than a solid cylinder's 1/2 mr squared, the rotational inertia of a hollow sphere would be greater than that of a same mass solid sphere for the same reason. The mass of the hollow sphere is farther from the center. A thin spherical shell has rotational inertia of 2/3 mr squared, or 1.66 times greater than a solid sphere's 1/5 mr squared. Because all objects have the same shape, have the same laziness per mass ratio. Similarly, recall from Chapter 6 how the same weight per mass ratio of all freely falling objects accounted for their equal acceleration, A equals F over m. Just as objects of any mass in free fall have equal accelerations, round objects of any mass have the same shape, rolled down an inclined plane with the same acceleration. Concept check. What happens when objects of the same shape but different sizes are rolled down an incline? 12.4 Angular momentum. Anything that rotates, whether it be a cylinder rolling down an incline or an acrobat doing a somersault, keeps on rotating until something stops it. A rotating object has a strength of rotation. Recall from Chapter 8 that all moving objects have inertia of motion or momentum. This kind of momentum, which is called linear momentum, is the product of the mass and the velocity of an object. Rotating objects have angular momentum. Angular momentum is defined as the product of the rotational inertia I and the rotational velocity omega. Angular momentum equals rotational inertia times rotational velocity. The turntable in 12.12 has more angular momentum when it is turning at 45 RPM than at 33 1/3 RPM. It has even more angular momentum if a load is placed on it, so its rotational inertia is greater. I remember the 78 RPM records. Like linear momentum, angular momentum is a vector quantity and has direction as well as magnitude. When a direction is assigned to rotational speed, we call it rotational velocity. Rotational velocity is a vector whose magnitude is the rotational speed. By convention, the rotational velocity vector as well as the angular momentum vector have the same direction and lie along the axis of rotation. In this book, we won't treat the vector nature of angular momentum or even of torque, which also is a vector, except to acknowledge the remarkable action of the gyroscope. Low friction swivels can be turned in any direction without exerting a torque on the whirling gyroscope, as in figure 12.13a. The gyroscope in 12.13 is a remarkable device. A. The operation of a gyroscope relies on the vector nature of angular momentum. B. Angular momentum keeps a wheel axis almost horizontal when a torque supplied by Earth's gravity acts on it. As a result, it stays pointed in the same direction. Similarly, the rotating bicycle wheel in figure 12.13b shows what happens when a torque by Earth's gravity acts to change the direction of the bicycle wheel's angular momentum, which is along the wheel's axle. The pull of gravity that acts to topple the wheel over and change its rotational axis causes it instead to precess in a circular path about a vertical axis. You must do this yourself while standing on a turntable to fully believe it. Full understanding will likely not come until a later time. Figure 12.14 illustrates the case of an object that is small compared with the radial distance to its axis of rotation. An object of concentrated mass m whirling in a circular path of radius r with a speed v has angular momentum of mvr. In such cases as a tin can swinging from a long string or a planet orbiting in a circle around the sun, the angular momentum is simply equal to the magnitude of its linear momentum mv multiplied by the radial distance r. In equation form, angular momentum is equal to mvr, just as an external net force is required to change the linear momentum of an object, an external net torque is required to change the angular momentum of an object. Newton's first law of inertia for a rotating system states that an object or system of objects will maintain its angular momentum unless acted upon by an unbalanced external torque. We know it is easier to balance on a moving bicycle than on a resting one. The spinning wheels, such as those shown on the bikes in figure 12.15, have angular momentum. When our center of gravity is not above a point of support, a slight torque is produced. Figure 12.15, the lightweight wheels on racing bikes have less angular momentum than those on recreational bikes, so it takes less effort to get them turning. When the wheels are at rest, we fall over. But when the bicycle is moving, the wheels have angular momentum, and a greater torque is required to change the direction of the angular momentum. The moving bicycle is easier to balance than a stationary bike. Concept check. What happens to angular momentum when no net external torque acts on an object? Section 12.5, Conservation of Angular Momentum. Just as the linear momentum of any system is conserved if no net force acts on the system, angular momentum is conserved for systems in rotation. The law of conservation of angular momentum states that if no unbalanced external torque acts on a rotating system, the angular momentum of that system is constant. This means that with no net external torque, the product of rotational inertia and rotational velocity at one time will be the same as at any other time. Angular momentum is conserved when no net external torque acts on an object. An interesting example of angular momentum conservation is shown in figure 12.16. The man stands on a low friction turntable with weights extended. Because of the extended weights, his overall rotational inertia is relatively large in this position. As he slowly turns, his angular momentum is the product of his rotational inertia and rotational velocity. When he pulls the weights inward, his overall rotational inertia is considerably decreased. What is the result? His rotational speed increases. This is best appreciated by the turning person who feels changes in rotational speed that seem to be mysterious. But it's straight physics. This procedure is used by a figure skater who starts to whirl with her arms and perhaps a leg extended, and then draws her arm and leg in to obtain a greater rotational speed. Figure 12.16, when the man pulls his arms and whirling weights inward, he decreases his rotational inertia and his rotational speed correspondingly increases. Whenever a rotating body contracts, its rotational speed increases. Similarly, when a gymnast is spinning freely, as shown in figure 12.17, angular momentum does not change. However, rotational speed can be changed by making variations in rotational inertia. This is done by moving some part of the body towards or away from the axis of rotation. The cat shown in figure 12.18 is held upside down and dropped, but is able to execute a twist and land upright even if it has no initial angular momentum. Zero angular momentum twists and turns are performed by turning one part of the body against the other. While falling, the cat rearranges its limbs and tail. Figure 12.17. Rotational inertia is controlled by variations in the body rotational inertia as angular momentum is conserved during a forward somersault. Figure 12.18. After being dropped upside down, the cat rotates so it can land on its feet. Repeated reorientation of the body configuration result in the head and tail rotating one way and the feet the other, so that the feet are downward when the cat reaches the ground. During this maneuver, the total angular momentum remains zero. When it is over, the cat is not turning. This maneuver rotates the body through an angle, but does not create continuing rotation. To do so would violate angular momentum conservation. Humans can perform similar twists without difficulty, though not as fast as a cat can. Astronauts have learned to make zero angular momentum rotations about any principal axis to orient their bodies in any preferred direction when floating in space. Concept check. What happens to angular momentum when no net external torque acts on an object? 12.6. Simulated gravity. In Chapter 10, we considered a ladybug in a rotating frame of reference. Now consider a colony of ladybugs living inside a bicycle tire as shown in figure 12.19 below. If we toss the wheel through the air and drop it from an airplane high in the sky, the ladybugs will be in weightless condition and seem to float freely while the wheel is in free fall. Now spin the wheel. The ladybugs will feel themselves pressed to the outer part of the tire's inner surface. If the wheel is spun at just the right speed, the ladybugs will experience simulated gravity that feels like the gravity they are accustomed to. Figure 12.19. If the spinning wheel freely falls, the ladybugs inside will experience a centrifugal force that feels like gravity when the wheel spins at the appropriate rate. From within a rotating frame of reference, there seems to be an outwardly directed centrifugal force which can simulate gravity. Gravity is simulated by centrifugal force. To the ladybugs, the direction up is towards the center of the wheel. The down direction to the ladybugs is what we call radially outward, away from the center of the wheel. Need for simulated gravity. Today we live on the outer surface of our spherical planet, held here by gravity. Earth has been the cradle of humankind, but we will not stay in the cradle forever. We are on our way to becoming a spacefaring people. In the years ahead, many people will likely live in huge, lazily rotating space stations where simulated gravity will be provided so that people can function normally. Support force. Occupants in today's space vehicles feel weightless because they lack a support force. They're not pressed against a supporting floor for gravity, nor do they experience a centrifugal force due to spinning. But Future space travelers will not be subject to weightlessness. Their space habitats will probably spin, like the ladybug's spinning bicycle wheel, effectively supplying a support force and nicely simulating gravity. Spiral galaxies linked to astronomy. The shapes of galaxies, such as our Milky Way, have much to do with the conservation of angular momentum. Consider a globular mass of gas in space that begins to contract under the influence of its own gravity. If it has even the slightest rotation about some axis, it has some angular momentum, which must be conserved. As the gas contracts, its rotational inertia decreases. Then, like a spinning ice skater who draws her arms inward, the ball of gas spins faster. As it does so, it is flattened, just as our spinning Earth is flattened at its poles. If the glob has enough angular momentum, it turns into a flat pancake with a diameter far greater than its thickness and may become a spiral galaxy. The interaction between the man and the floor of the space habitat as seen at rest outside the rotating system is shown in figure 12.20a. The floor presses against the man action and the man presses back on the floor reaction. The only force exerted on the man is by the floor. It is directed towards the center and is a centripetal force. As seen from inside the rotating system in figure 12.20b, in addition to the man-floor interaction, there is a centrifugal force exerted on the man at his center of mass. It seems as real as gravity, yet, unlike gravity, it has no reaction counterpart. There is nothing out there that he can pull back on. Centrifugal force is not part of an interaction, but results from rotation. It is therefore called a fictional force. Figure 12.20, the man inside this rotating space habitat experienced simulated gravity. A, as seen from the outside, the only force exerted on the man is by the floor. B, as seen from inside, there is a fictitious centrifugal force that simulates gravity. Challenges of simulated gravity. The comfortable 1g we experience at Earth's surface is due to gravity. Inside a rotating spaceship, the acceleration experienced is the centripetal acceleration due to rotation. Notes: the idea of a rotating space station to keep astronauts' feet on the floor, wonderfully shown in the 1968 movie 2001: A Space Odyssey, and in Arthur C. Clarke's 1973 book, Rendezvous with Rama, is credited to the Russian scientist Konstantin Tsiolkovsky in 1920. The magnitude of this acceleration is directly proportional to the radial distance and the square of the rotational speed. For a given RPM, the acceleration, like the linear speed, increases with increasing radial distance. Doubling the distance from the axis of rotation doubles the centrifugal acceleration. At the axis where radial distance is 0, there is no acceleration due to rotation. Small diameter structures would have to rotate at high speeds to provide a simulated gravitational acceleration of 1g. Sensitive and delicate organs in our inner ears sense rotation. Although there appears to be no difficulty in a single revolution per minute, 1 RPM or so, many people have difficulty adjusting to rotational rates greater than 2 or 3 RPM, although some people easily adapt to 10 or so RPM. To simulate normal Earth's gravity at 1 RPM requires a large structure, one almost 2 kilometers in diameter. This is an immense structure compared with the size of today's space shuttle vehicles. Economics will probably dictate that the size of the first inhabited structures be small. If these structures also do not rotate, the inhabitants will have to adjust to living in a seemingly weightless environment. Larger rotating habitats with simulated gravity will likely follow later. Imagine yourself living in a rotating space colony such as the one shown in figure 12.21. If the structure rotates so that inhabitants of the inside of the outer edge experience 1g, then halfway between the axis and the outer edge, they would experience only 0.5g. At the axis itself, they would experience weightlessness at 0g. The possible variations of g within the rotating space habitat holds promise for a most different and yet unexperienced environment. We could perform ballet at 0.5g, acrobatics at 0.2g, and lower g states. Three-dimensional soccer and sports not yet conceived in very low g states. Figure 12.21, this NASA depiction of a rotational space colony may be a glimpse into the future. People will explore possibilities never before available to them. This time of transition from our earthly cradle to new vistas is an exciting time in which to live, especially for those who will be prepared to play a role in these new adventures. Concept check. How is gravity simulated? Rotational motion. The greater an object's rotational inertia, the more difficult it is to change the rotational speed of the object. The three principal axes of rotation in the human body are the longitudinal axis, the transverse axis, and the medial axis. Objects of the same shape but different sizes accelerate equally when rolled down an incline. Newton's first law of inertia for rotating systems states that an object or system of objects will maintain its angular momentum unless acted upon by an unbalanced external torque. Angular momentum is conserved when no net external torque acts on an object. From within a rotating frame of reference, there seems to be an outwardly directed centrifugal force which can simulate gravity.